Cloud team. All right, so in our previous lecture, we were talking about the matrix norms, right? So if I can write it down over here, let's say we considered matrix norms. And we saw that you can define matrix norms in different ways. We majorly talk about two different ways. So the one way was to unwrap the matrix into a vector and consider the matrix as a vector, right? So consider the matrix as a vector. And we already have the definitions for the vectors, right? So we can talk about the infinity norm then. So if you represent this A matrix by its entries, let's say Aij, okay, the infinity norm of the matrix will be simply equal to the maximum absolute value of its elements, right? So it will be something like this. So I unwrap the A matrix entries into a vector and use the vector norm definition here. Or similarly, you can define the L1 norm of the matrix by saying that it will be simply equal to summation of its absolute value of its entries. And we also mentioned that, okay, you can do that for the L2 norm, which was, again, this double summation Aij square. And we said that, okay, this is also equal to, in the previous lecture, trace of A transpose A. And that had a special name. What was it? That thing was called the Frobenius norm of the matrix, right? And we said that, okay, we can generalize this idea to P norms. So we can define the P norm of a matrix as the unwrap the matrix into a vector and apply the vector definition, vector norm, P norm definition. So you can simply write that for P greater than 1, right? Sorry, not equal to infinity. So that was one way of defining the matrix norms. And another way was to use induced norms. So we didn't have chance to talk about it much. We said that, okay, there is another way, and that is induced norms. So here we, in the first part, we considered the matrix as a vector, okay? So this time the matrix is going to stay as a matrix, okay? But we are going to use the vector norm definition. So we can define matrix norm using vector norm definitions, let's say. Okay. So this is actually induced by, you can also say, instead of using, so that's the reason why we have the induced norm. All right, we said that, okay, then we can define this norm of a matrix as the maximum over all possible x's in this Rn, such that x is different than the zero vector. We would like to find the maximum value of norm Ax divided by norm of x. Okay. And if this is an m by n matrix, the A times x is going to be m-dimensional real vector. So this is in Rm, and sorry, m by n, and this is in Rn, right? X is in Rn. So we said that this is one definition of the induced norm, but we also have an equivalent definition. We show that you can also define the same induced norm as among all the x's which has unit norm, we are looking for the maximum value of the norm of A times x. Okay, and we also saw some animations about it in the lecture slides. So these are basically the two ways of defining matrix norms. And in our next example today, where is it? Somewhere over here. Okay, we show that this is induced norms enjoy certain properties such that AX is always smaller than norm A times norm X. And we also investigated how to define them by using different norm definitions of the vectors. And finally, we were trying to solve one example. So we just wanted to apply the induced norm definition for, let me write down the definition, by using the infinity norm of the vectors in Rn and Rm. Okay, so what we would like to do is this. We would like to find the maximum of this guy. So for among all x with norm equals 1, but this is the infinity norm. We would like to maximize the infinity norm of AX. Okay. So in order to go into details of that guy, I will show you one example. Okay. By the way, do you have any questions that I can answer shortly? Anything that I can explain further? Then let me continue, okay? So before finding the induced norm of a matrix by using the infinity norm definitions of the vectors, both here and there, I would like to show you one example. Okay, so consider the A matrix. Let's say it is 1, -2, -3, 4, -2, and 2. Okay, and so A is a 3x2 matrix. Okay, so you get you get vectors in R2 multiplied by A, and the AX is in R3, right? So that kind of maps a vector from R square to R cube there. Okay. So what I would like to do is that how should we choose this x vector? So we are looking for among all the x vectors with norm equals 1, we want to maximize AX, okay, with the infinity norm. So I want to show you what should be our general approach, okay? For that thing, let's have a look at the first row of A, okay? So we write as that's look at the first row of A. So I will call that guy as A bar, and that is simply equal to 1 and -2. And suppose I want you to maximize A bar times X. Okay, so A bar 1 -2 and X1. X is in X1 and X2. So I want to maximize that multiplication while keeping infinity norm of X equal to 1. Okay. So how can we maximize that thing? So first note that if what is the definition of the infinity norm? So for two-dimensional vectors, that is simply equal to maximum value of absolute value of x1, absolute value of x2. Okay, and that thing being equal to 1 means that either x1 or x2 is equal to 1 or -1. And the other variable is something between -1 and 1. Somebody was asking a question, I guess. Any questions? Okay, maybe that was just a noise from the microphone then. Okay, so suppose I would like to maximize these two multiplication, okay, and the infinite norm of the result of this multiplication. So that will be simply equal to what? X1 minus 2x2, right? So can you tell me one x which maximizes the absolute value of that guy? So how would you choose x whose infinite norm is equal to 1 and maximizes the absolute value of that guy? So one candidate, for example, would be I can choose x1 equals 1 and x2 equals minus 1, right? And in that case, this will amount to 3, right? Then I will get the maximum contributions from each term in this addition operation, right? How about another alternative x? Can you name another that maximizes this absolute value? Wait, let me put the absolute value of that guy over here as well.
The negative of this.
Exactly. So another x can be minus 1 and 1, right? So then I will again end up with 3. Okay. Okay, so if I consider a bar and if I try to find the induced norm of a bar, which is by definition maximum among all the x vectors which infinite norm equals to 1, I am looking for the norm a bar times x infinity, and that is equal to 3. Okay. By the way, I'm picking up a sound from one microphone, so maybe you can, if you can mute yourself, it would be better. Thank you very much. All right, so we can pick particular x's over there, and we can say that the norm of a bar in this norm of a bar is equal to 3, right? So if I follow the same idea and apply to the A matrix itself, okay, so 1 minus 3 minus 3, 4 minus 2 and 2 times x1 and x2, okay? So I would like to maximize let me write it in another color. Where is it? So I would like to maximize the infinity norm of a times x. This is a and this is x, okay? So what can I choose x1 and x2 to maximize that value? So notice that if I pick x1 to be equal to 1 and x2 equal to minus 1, then I will get the maximum absolute value from each of these rows as 7, right? So I write it down as I can find norm of A to be equal to 7 when x is equal to minus 1 and 1. Do you all agree with that? I mean, I can maximize the contribution from each row, right? So with different by choosing different x values, and the maximum value that I can get is from second row, because the absolute value of the sum of its elements is maximum at the second row, right? And the x vector which maximizes that sum is either minus 1 and 1 or 1 and minus 1, right?
Hocam bir şey sorabilir miyim acaba?
Tabii, buyurun. Hı hı.
1'e eksi 1 seçtik ya, maksimum değeri 1 dedik. Hani ikisi de aynı ya. Hani o maksimum değeri olabilir mi ki? Absolute değerleri.
So this is the maximum value of absolute value x1, so both of them can be ones, both of them can be -1, right? Is that what you're asking?
Evet hocam, bunu soruyordum aslında da.
So both of them can be 1 and 1, 1, -1, -1, and still that the norm of that vector is going to be equal to 1, right? So remember that what was the unit sphere for the infinity norm? As you might remember, so we taught that at the very beginning of the lecture. It was like a square like this, right? This is 1, this is -1. So all these corners are also included in this unit sphere. These are the 1, 1, and this is the -1 point. So these are all vectors with norm, the infinite norm being equal to 1, right?
Teşekkürler hocam.
Okay. So if we multiply this a times x, we will get this, each of these rows multiply for these two, and I will get a 3 by 1 vector, okay? And I will pick the value with the maximum absolute value of these multiplications. And I can get the maximum on the second row over here if I pick x as either -1, 1 or 1 and -1 to be the infinity norm of the, sorry, induced norm of a to be equal to 7. So next I do have a claim done. So our claim is that the induced norm of A with the with the vector infinity norm definitions for the vectors is equal to maximum absolute sum of these elements. So it will be, the row sum. So j from 1 to n absolute aij. So you pick the investigate each row of the A matrix, and you pick the maximum of the sum of the absolute values of this matrix.
Hocam maksimumun altında ne yazıyor acaba?
So it is 1 I from 1 to n. Okay. So this is the ith row, and you sum the elements on the ith row. Okay, so we are going to try. Sorry, we will try to show that. Okay, so let's try to do that. So in order to do that, I will first write, as you see over here, so it is related to rows of the A matrix. So I will try to write down the A matrix as rows. Okay, so let me write the A matrix as R1, R2, and Rn. Okay. And if that is the case, the A times x is equal to R1 times x, R2 times x, and Rn times x. Okay. And any ith row of the A matrix can be written as this vector A, I1, A, I2, A, I. Okay. Then, if that is the case, what you would like to maximize is that you would like to maximize the infinity norm of AX, right? So that is maximizing for each row absolute value of Ri times x. So because this is the resulting vector, and we are trying to maximize the absolute value of that thing. All right, so in order to make our proof, so we assume that this is maximized for the kth row, okay, and for some vector z, I can get the maximum value of that thing. Just like, for example, in the previous example, that the kth row was the second row, and the special vector was this -1 and 1, so that I could get 7. So there's always a maximum of that thing, right? So let's assume that that is the kth row, and there's a vector whose norm is equal to 1, that the infinity norm of that vector is equal to 1. Okay. So let me try to write it this way. So let's assume maximum of that thing while norm of x infinity equals to 1, norm ax infinity is equal to absolute value of rk times z for some z, okay? So z rm with norm z infinity equals 1. And k is the row, so k is a number between 1 and m, okay? So that is for some k between 1 and m. Okay. So in that case, the induced norm of that matrix A will be simply equal to absolute value of rk times z, right? And if I write that thing as the element by element, so it will be simply equal to absolute value of ak1 z1 plus ak2 z2 plus akn zn, okay? So that is not the kth row of the A matrix. I write it as ak1, ak2, akn, etc. All right, then I can claim that that absolute value is less than or equal to absolute value of the individual elements. Akn, absolute value. Okay, and furthermore, that is equal to absolute value of ak1 z1 is absolute value of ak2 z2 plus absolute value of akn absolute value of zn. Okay. So notice that we said that the norm of z is equal to the infinity norm of z is equal to 1. Okay. So that means that so since infinity norm of z is equal to 1, we must have absolute value of these elements of z must be less than or equal to 1. Okay. So therefore we can write, that sum is less than or equal to absolute value of ak1 plus absolute value of ak2 plus absolute value of ak. So that is the sum of absolute value of the elements of the kth row of A matrix. And so that is also less than if I trace all the rows of A. So that is also less than max 1 to m summation j from 1 to n, absolute value of a ij. Okay, so that sum is less than the maximum value of that sum for each of these rows. Okay, and then by doing so, we show that this induced norm of A is less than or equal to maximum value over I summation j from 1 to n, absolute value of A I j. So that was actually the first part of our proof. Then I will continue with the second part. So let me write that thing as the first equation. Okay. So in this proof, we will first show that maybe I can write it explicitly so it will be clear for you as well. So we will first show that norm A is less than or equal to its maximum to m summation j absolute aij. Okay. And in the second part of the proof, I will show that norm A is greater than maximum 1 to m summation j absolute aij. Okay. And if something is less than a number and greater than a number, greater than or equal to, less than or equal to a number, that will conclude that the norm of A is equal to that expression over here. Okay. So we just showed the first part that norm in this norm of A is less than that value over here. Do you have any questions? At this part, I can explain further. So we just said that, okay, so suppose that infinite norm is maximized for the kth row, okay? Then if that is maximized at the kth row, there is a vector z such that if you multiply those two guys, the infinite norm is is equal to such an expression over there, okay? And by using the properties of the absolute value, we show that that multiplication is less than when z infinite norm of the z vector is less than or equal to 1, that multiplication is less than the absolute value of the row sum, sum of the absolute value of the elements in that kth row, okay? And that is smaller than the sum of the absolute value of the elements in any row. That's what we just said. If this is true for k, so that is that should be less than the maximum value of that thing. Okay, so in the second part, we will show that the maximum value of this absolute row sum is less than the norm of A. So I will do that, but I don't have space here, so I will jump to the summary notes if I can. Maybe not, huh? Okay, good. I have enough space there, so I will continue over here. Okay. There's the editing part 2. Let's continue from there. Okay, so now suppose this time we have the maximum absolute value of the elements is happening at the alto. Okay, so maybe I can write in blue. So let's be such that the maximum value of these absolute sums is happening for the alt row, okay, is corresponding to j from 1 to n absolute value of a l j, okay. Or let me write that explicitly. So the else row has the maximum absolute row sum. Okay. So what we will try to do is that I can get the maximum row sum, so sum of absolute values of this row by multiplying that row with a specific vector. So I will write down the vector, and maybe you might agree with me. So now consider the vector that y b r n such that y is equal to sine of a l1 sine of a l2 and sine of a ln. So if AL1 is a positive number, then the sine of AL1 is equal to 1. If AL2 is a negative number, then sine of AL2 is equal to minus 1. Okay. So that is a vector composed of ones and minus ones, or zeros. Okay. So first of all, notice that the infinite norm of that y vector is equal to 1, right? So write as, notice that infinite norm of y is equal to 1. Okay. And then I can write, so that I can get this absolute sum as the sum multiplication of that vector with this y vector over here. I mean the multiplication of the alt row with the y vector. So I'll write it in this way. So we can write maximum 1 to n summation I from 1 to n absolute value of aij, which was equal to summation j from 1 to n alj. So j from 1 to n absolute value of alj as summation j from 1 to n alj times sine of alj. Okay. And that way this sum is going to be equal to, since all of these numbers are going to be positive numbers, I can say that that will be equal to j from 1 to n alj sine of alj in absolute value. Okay, so this was simply equal to the absolute value of the alt row RL times y. Okay. So this is the alt row. Can emphasize once again. Okay. So next I can claim that if this is RL times y, that thing is smaller than the maximum, so 1 is the I m times So L is already included among these values, so that has to be less than maximum of Ri times Y, right? And that was simply, this is the definition of the infinity norm of AY, right? So this is A times Y infinity norm. So just like in the first part, this multiplication ends up with Ri times X for each of these. And the maximum value of these values is going to be the infinity norm of A times Y. Right? I can write it explicitly. A times Y is equal to times Y, 2 times Y plus M minus Y. And we also picked a specific Y vector such that the infinity norm of Y is equal to 1, right? So that expression I had at the end, so let me write it down first. So note that infinity norm of Y is already equal to 1. So that value has to be less than maximum value among all x's with infinity norm equals to 1 norm ax infinity. And that is, by the way, the definition of the induced norm of A, right? Okay. So remember that we start from that maximum value, or let me say that, show you the expression. We said that, okay, then we said that this expression is less than or equal to the induced norm of A, okay? So we simply show that induced norm of A is now greater than maximum of summation J from 1 to N absolute A at J. And I will say that that's the second equation, okay? And in the first equation, we show that norm of A is less than this value, less than or equal to that value. In the second part, we show that induced norm of A is greater than or equal to this value. So then I can conclude that from equations 1 and 2, the induced norm of A is equal to max summation J from 1 to N, absolute value of A at J. So that was the reason why we have, where is it? In the first example, this was our A matrix, and the maximum value of the sum of absolute value of its row elements is maximized on the second row, right? So that is the second row, and the induced norm of A was equal to Y. Oh, sorry, 7 over there. And that is corresponding to this expression over here. And we show that is indeed the induced norm of A matrix by proving our claim by showing that norm of A is less than or equal to that expression and is greater than or equal to that expression, so it has to be equal to that expression. So I wish we had this lecture in classroom, the face-to-face, so that you could ask me the parts that you didn't understand. So I know it is a bit difficult to ask in an online lecture, but please do ask the part that confuses the most. I can explain a little at least.
Hocam ben sadece ilk mutlak değer koyduğumuz yer vardı ya son sayfada.
Part 1 mı, part 2 mu?
Part 2.
Okay, so let's go to the part 2 here. Yes.
Burada
So-
kırmızıyla altın çizdiniz ya hocam. Oradan sonraki 2 adım sonra mutlak değer koyduk ya.
Şurayı mı söylüyorsunuz?
Evet.
So this is the sum of the positive numbers, right? So whether this guy is negative, I multiply with -1. So therefore I am summing up all positive numbers here, right? And if I'm summing up all positive numbers, I can write that thing as the absolute value of the sum of individual elements. It's like if every individual element is a non-negative number, right? So I'm just saying that 1 plus 3 plus 5 is equal to absolute value of 1 plus 3 plus 5. Okay. The summation will be non-negative, so I was able to put that. But that's a good question. So let me erase that part. Confused them. Very good question. Any other such transitions between the lines that you would like to ask? Anyway, so let's do it like this. So just have a look at this lecture once again, maybe to the video. And if you still have some question marks, just contact me, okay, by email, so we can arrange a session and go through the derivation once again. All right. So if something bothers you, just contact me so that we can arrange a session and have a look at it together. All right. So the next topic that we will continue is the convergence concept, but we can continue that after a break, a 10 minutes break. Okay. So I will stop recording here. Where is it? If I can.